Hi guys, this video might be a little bit different than the other one in the channel. In this one, I'm going to present one of my projects during my PhD, and I will talk about the exact reasons of why did I choose this specific architecture and go a little bit into the details. So it might be a little bit technical. So without further ado, let's jump right into it. Welcome everyone to your channel, AI Fun Fact for All. For those of you who are new to this channel, my name is Pedro Magan. I have a PhD in computer science and I have extensive knowledge in AI and machine learning. And in this channel, we talk about the machine learning in our everyday life and how we can use it to maximize it. In this video, I'm going to present an autonomous driving project. I have used a transformer architecture and use it in order to develop an end-to-end approach in Carla simulator that will do the perception all the way to control in an end-to-end approach. And it's going to be a little bit technical. We're going to use the transformer architecture, the backbone in ChatGPT and other large language models, and we're going to see from a technical standpoint how you need to look at the different part and what are the benefits of each of them and what is the future direction. DMFuser distilled multitask learning for end-to-end transformer-based sensor fusion in autonomous driving. Let's look at intro. Sensor fusion for imitation learning lacks effectiveness in dynamic scenario when we have different cars or different adversarial happening inside the scenario. So we have DMFuser, which is an autonomous driving with a student-teacher architecture and use a transformer with knowledge distillation. We have two base modules. The first one is the perception one, which encodes the input data into a semantic depth cloud using the attention CNN. So it's used as a representation learning. And then we have the control module, which decodes the feature, maybe the simulator for predicting waypoint and final control in feature space. So it has a hybrid approach. Now, first, let's talk about the perception module. As I said in the beginning, the perception is the representation learning part, which we are using the CVT, which is an architecture an extension of the VIT by the Microsoft that is used for better extracting image feature. It should use a combination of the CNN and convolution module, and we are using that inside our method as well. So we are going to have a semantic depth cloud for better recognizing the objects in the environment. So this semantic depth cloud uses the depth information and the semantic segmentation in order to generate a top-down view, and it's going to be very useful for our control module. Now we are going to use combined convolution and attention to extract features locally. So the CNN is very good in extracting features locally, and then maybe use the attention to extract the features globally. So we are using the depth images and semantic segmentation to create 23 layers of bird's eye view map. That's basically the different segments that we can see in a scenario that happens outside. Now let's take a look at the overall architecture. Everything in here is color coded. The blue one are actually for the perception and the green are for the control module, and then we have the yellow one, which are actually our output. So if you're looking from the beginning, we have the RGB image from the left, right, and front. That goes to our encoder, which we are going to use a pre-trained CVT, and then it will go in a unit architecture and will done the simple process of decoder to generate the semantic segmentation. So the semantic segmentation will also be left, front, and right, 23 different layers, and we create this basically RGB features. And then the RGB feature, which actually go to two different heads for a speed head and traffic light control head, which basically try to predict them. And then it will also go to the attention CNN fusion module, which we'll talk about it shortly. And then we can also see that from this semantic segmentation, in addition to the depth image, which are actually also an input, as we see is orange, we are going to create this bird's eye view. So this is not going to be learned, it's basically a function that will create this bird's eye view. So this bird's eye view will go to another encoder, an efficient net, and it will create the attention CNN. So this is something that I will talk about it shortly. And then the result of this attention CNN will create a abstraction of what is happening inside the whole environment, and then it will go and concatenate with our speed, route, and command. This is again orange, which is another input that we get, and we add to our system, and it will go into two separate modules, which we talk about. It is waypoint prediction and the navigational prediction. As I said, it's a hybrid approach. It has end-to-end and also PID on the fly. And then the prediction one from the waypoint will also have some insights to the end-to-end, and finally we will generate the steering, throttle, brake, and waypoint. So the yellow box in here are the single task of each of the outputs of the target variable that we want, and it's a clone of the right side, but the only thing is that it is single task, so it is only training one of them at the same time, and it will be acting as the teacher in a student-teacher architecture. So when we are training waypoints in here, we are not training the other three, and then if there is any interfering, it will be avoided. And then we are going to use the adaptive feature matching, which basically try to use another layer of pseudo labels to kind of train our multitask head in here, which try to train all of them at the same time, and try to basically find a distilled version of these 4 separate nodes that have single tasks. So for dataset, we are using the Carla simulator 9.10, and we have trained over 350k frames that are generated from the DMFuser paper. The only difference is that we changed the camera from 2.3 meter to 1.8 meter for better scene observability. For the train, we use 8 publicly available towns for both short and long scenarios, overall 2500 roads and all weathers. And for the test, as the convention, we are using the town 5 short, long scenarios, and then we're also considering adversarial situation, which act some abnormal NPC behavior, and then we have some normal condition as well, and all the different weather conditions. Here we can see the detail of the architecture that we already talked about. We are gonna dive deep into the attention CNN and basically the control loops. So here we have input the RGB to the CVT, and then we get the RGB features, and the RGB features are going to be concatenated with the efficient net, which actually generated from the semantic depth cloud. And this one, the concatenation is going to go into our attention CNN block. It's heavily inspired by the CVT paper, and we are going to have in the beginning a batch normalization layer, which is going to balance the 2 separate inputs that comes in, and then we're going to use a conventional multi-head attention. So we have the pair of query and keys and values, and then we have multi-head self-attention, and then we have this basically residual module, and we have the normalization and NLP. So this is basically our attention block, and after that we are going to have the CNN block to do the local consideration of the inputs in the image. So we have the convolution 2D, the normal, average, pulling, flatten, and then finally the linear. So this one is going to be concatenated now with extra information such as the speed, route, and the command. So the command is some general information, and route is also some general information like a GPS location, and it doesn't have a very good precision, so it's like a horizon of, like, for example, 150 meters or so. And then this will create our fuse feature. So the fuse feature will actually go into our 2 different loops, and the first one on the top is basically our waypoint, which is going to use a GRU loop that try to kind of like make this autoregressive more the process of this autoregressive more correct, and then it will actually generate the waypoints for us. And we are going to also use this waypoints feature that we generate in here and add it to our basically control module. So the control module in here again have the loops which try to predict 3 times in future, same as the waypoints, and then we're just going to use the first one, but we predict 3 times because we want to learn a little bit about the dynamic of the system. So again, very similar architecture to the GRU. Is just going to have the information from the waypoints that kind of encapsulates some static features of the environment, such as, for example, the lanes, or the for example the curb and areas like that. And this one, the loop on the bottom, will try to learn the dynamic features such as the vehicles, other vehicles that are passing, or any passenger that is going by. It will be captured from the second one, and as the output it will predict the brake, steering, and throttle. Knowledge distillation and multitask learning in here, I will talk about the AFM or adaptive feature matching that we use for the separate basically single task networks that are used as a teacher, and we'll try to learn our multitask basically network, which is basically the student that we have. So we try to use this bottleneck network and try to use some pseudo labels and try to minimize the distance between these networks. So we have done a little bit of ablation studies in here. We can see the vanilla DMFuser. In here we can see some more results in terms of basically some specific tasks. So if we remove for example the attention, it's not going to have that much effect on the braking, but the other parts are going to be worse. And then the same for removing the vehicle vertical control or the distillation module, which have an importance on the throttle. And if we actually don't remove anything, you see that this is our method, which basically is good in almost all of the different single task architecture. And here is the overall score. So if we do them on basically the hard weather conditions, so when there's a hard rain or basically sunset, so the vision is not very good, we can see that the method that nothing is removed provide the highest driving score. That is basically what we are trying to optimize for. And then the other one will actually lack in some other features. So we also have done the final result in here. We have done the comparison of clear noon and all weather clear noon long and clear and all weather long for both normal and adversarial situation. Basically, both in long and short, we actually provide the best result. And we can see that on the long, we actually outperformed the other approach by a larger extent. And the reason is because our approach is trying to balance the road completion and don't jump into conclusion or making some aggressive actions. I also want to take a look at this quantitative result in here. So on the first image on the left, we can see a situation where the pedestrian cross suddenly. As we can see in here, we have two different controls. So we have the green, which is actually the MLP control or the end-to-end control, and then we have PID. So these two are actually not similar, but we obviously know that we have to do the brick, and PID can do this faster compared to MLP, and that's why our overall control, which is a combination of them, will detect this and will actually obey the PID control. On the other side, for example, when we are turning left, in here we can see the PID is doing completely, for example, brake, but then the MLP have the throttle and a little bit of a steering, and we can see that MLP, the overall architecture is actually listening to MLP now, because when we are doing the kind of like a difficult situation which requires a lot of maneuvering and throttle and steering, the end-to-end approach is more reliable. At the beginning, we have the normal or weather scenario. On the top, we have all the images, basically the oracle of knowledge, and then on the bottom of it, we have the semantic segmentation, and we have below it the image that we actually feed into the network, because we don't feed everything to our network. And on the right side below, we can see basically our top-down view, and we have the waypoint. So you see that the three dots are actually the waypoints, and then the empty circle is basically the one that the command will actually give us. And then we have a normal, short, clear noon. So the short scenario are basically the scenario where we are just changing lane, or we are gonna stop behind a vehicle, or we want to just do a simple left turn or right turn. So let's focus on the shorter term approaches. And here on the semantic depth scale, you can also see the different maps as well. So for example, the pink are actually the traverse paths, and then the green are the vegetarian or vegetables that we should avoid, and the blue are the vehicles. And then here we see the adversarial situation. So the adversarial, suddenly you see a pedestrian comes by, or for example, you see a bicycle and so on. So very difficult situation that happens, and then it obviously doesn't train for that. And there you have it, guys. I went over the paper DMFuser, and we talk about the different architectural choice and the features and benefits of this approach. We talk about the different concepts behind it and what are the limitations and what we can do in order to further improve it. If you enjoyed this type of video, make sure to like it and consider subscribing to the channel. If you want to see more videos like this, make sure to watch this video that I created before, and I talk about how to use RL in an sparse reward setting, and I also talk about the coding and how to implement it. And I also created another video for the model, which actually how to get the results of depth information from one singular camera. Thanks for watching until the end of the video, and see you until the next one.